then, and we have a first step of n equals 1, what we get is, it's like a domino effect. Once the first one goes, they all go. And we're trying to prove the they all go part. So our original question is 1 plus 3 plus 5 plus 2n minus 1 equals n squared. So let n equal 1. Is that going to be, will this formula hold? Well, 2n minus 1 is 2 times 1 minus 1, which is 1. So on the left side of the equation, we end up with 1. And on the right side, we have 1 squared, which is also 1. 1 equals 1. So it is true for n equals 1. Okay. Now we're going to look at an assumption. So now we will assume true for n equals k. Whoops, not 2n, 2k. And we're going to say, hey, that's going to be equal to k squared. Okay, there's our assumption. Now the last step is, what happens with k plus 1? Assuming that this part is true, what happens at the next step, the next iteration? So we have 1 plus 3 plus 5. I got to pay attention to my parentheses there. I've got an extra k plus 1. And I'm going to say, hey, is this equal to k plus 1 squared? And I put a question because we don't know that yet. All right. So this is kind of where things can get kind of slick. Obviously, we have this dot, dot, dot. A whole bunch of steps all the way up to this k, in fact, k plus 1. And we don't know how many are in there, what those numbers are, but we know that they increase through all the odd values. And this is sort of a trick. I'm going to think about the number just before this 2 times k plus 1 minus 1. Well, that's going to be this right here. Okay, so I'm just sort of like undoing some of these dot, dot, dots, and I'm putting one more value in, 2k minus 1. You might see that, hey, this whole part here, that's the same as this part from our assumption. So I'm going to replace all of that with k squared. Okay, let's see what we can do algebraically here to simplify some of this. This is k squared plus 2k plus 2, that's distributive property, minus 1. That's k squared plus 2k plus 1. Well, this is a trinomial that's factorable. This is equal to k plus 1 squared, which is what we are trying to prove. So going back to our proof by induction, we check to see, is it true for n equals 1? Yeah, that was right here. Step 2, assume it's true for, assume it's true for n equals k. All right, that's easy to do. You put a check because you're just making an assumption. And then step 3, what about k plus 1? Now, if k plus 1 is true, which it is, then you have finished the proof by induction. So the first n odd integers is equal to that number of odd integers squared.